Okay, in this video, we're going to go ahead and cover section 3.1, exponential functions and their graphs. This is the first part of unit 3, which deals with exponentials and logarithmic functions. So these two functions are going to be some of the non-algebraic functions that we see. They're actually called transcendental functions. Okay, just so a little bit of background information there. So let's start right off the bat with a definition. We have here that an exponential function f, okay, with a base of a, so our base is going to be a in this textbook, is written as the following. F of x is equal to a of x, okay, where a is bigger than 0 and a is not equal to 1, and x is any real number. Okay, so it has to be greater than 0, otherwise this will not work because you cannot put a negative base here for our a, and a cannot equal to 1 because if you put a 1 here, basically 1 to the power of anything is just 1. You're going to have a straight line. So we can't have it, it has to follow these conditions. Okay? We're going to start right away with some examples, and this is just some calculator practice, just in case you don't know how to evaluate this. We have three different functions. Okay, f of x is equal to 2 to the x, then 8 to the power of negative x, and then 0.5 to the power of x. And then just some numbers you want to plug in. So you can actually do this with just your basic calculator on your phone, or if you have a a for function, you can do it that way also. So here's mine. I'm going to go ahead and put it sideways so you can see how it looks when it has the more options here. Okay, so for the first one, you would have 2 to the power of x. So this one's going to look like the following. You're going to have 2 to the power of 0.74 is what you're trying to plug in. Okay, so for this calculator, if you decide to use, your phone one, it would be 2, and then the power button is going to be, I believe, this little x to the y right here. And you're going to see that parentheses automatically pop up. If not, go ahead and put those parentheses. So 0.74. It's a little bit difficult because I'm just kind of looking at the computer screen, not so much my actual phone. And there you go. That's it. 2 to the power of 0.74. And that's what I have there. And it shows my answer is approximately 1.670. So this first one is approximately 1.670. Okay. This one's a little bit more confusing, maybe because it has a square root, but it's the same deal. So we're going to go ahead and do that again. Let me go ahead and show this as well. So we have 8. So my base power of 8, my base of 8 to the power of, and this part is negative. So make sure you put that negative in front. So negative and then square root of 2. So notice all the parentheses that are popping up here. That's parentheses is to cover the 2. So I'm going to close that one. And then this one is to cover the root here. Okay, but in this case, it kind of stays the same. Just be careful, keep track of your parentheses. I think I actually put an extra parentheses. No, that's all right, it still came out. So this is approximately 0.0528. Okay, you kind of get the idea. These are not that hard. They're just kind of showing you just in case you don't know. And then here's the last one. And obviously, if you have a better calculator than the one on your phone, you can use that as well. Just make sure you keep track of your parentheses. So here's the last one, 0.5 to the power of 1/8. Why not throw a fraction in there? So 1 divided by 8, and then close the parentheses, and there it is. So 0.917. Okay, so that's it for this part right here. Very simple. You're going to find that this first part anyway is not that difficult, hopefully. Okay, so there we go. All right, so now let's talk a little bit about the graphs of these functions because these are actually very, very applicable graphs. And they follow some pretty similar patterns. We have two different things going on here. Y is equal to a to the x, where again a is positive, positive and bigger than 1. And then we also have y is equal to a to the negative x. So there's some key distinctions here where we have one power is positive and one power is negative. The domains are the same. The range is the same. The y-intercept is the same. So you're saying, well, what the heck? What's different, right? The horizontal asymptote is also the same. So we have a horizontal asymptote at y equals 0. But you're going to notice here there's something slightly different, okay? This right here represents the function. This is like saying as y is going to 0, as we're getting closer to 0, okay, what is x? I'm sorry, as x is getting closer to negative infinity, this is what the function's doing. And same thing here as well. But notice that these are different, okay? This one is going to the left side. Remember, negative infinity means to the left, and this one's going to the right side. And the reason that is because of the way the graphs actually look, which is the bottom part here, is opposite. So you're going to see that your one with the positive exponent, this one is actually increasing, and it's doing so continuously. That's why we have our arrows going up. This is actually called an exponential growth. Okay, we don't really see that terminology in this textbook, but in your Algebra 2 classes, you might have seen this as exponential growth. Here we just say the graph is increasing, okay, because it's going up from left to right. So you can see again as we're going to the left side, negative infinity, if we go this way, the graph gets closer and closer to 0, which is why we have our horizontal asymptote at y equals 0. On the other side, we have the graph going the other way. Sorry if it's a little bit crooked. So now we're decreasing as we go from left to right, but you're going to see that the graph is getting close to 0 on the right side. Okay, so if you forgot what that means, guys, you might want to write that down. This right here means on the right side, okay, and this one is on the left side. So one of the key distinctions with these two graphs is that they're both approaching 0, okay, y equals 0, but it's going in opposite directions because this one is a growth or increasing, this one is a decay or decreasing. Okay, one final thing about these two graphs here, note here at the bottom, we're going to note that both of these graphs pass the HLT, which is our horizontal line test. So that means that they are one-to-one, okay, meaning they have inverses. And it also means that we can use this property to solve equations in a similar sense. Okay, so let's go ahead and look at an example of that. Okay, so we have an example here that kind of talks a little bit about that one-to-one property I just kind of mentioned, and this is applicable to equations. Okay, so just like the graphs, a is greater than 0, not equal to 1. And if this is the case, that means that our powers have to be the same. Okay, so for that to happen, we have to make sure we have the same bases. And you might have seen this also in your Algebra 2 class in the past. Let's go ahead and jump straight into an example. So we have 8 is equal to 2 to the power of 2x. What we want to do here is we want to make them the same base. So we're going to make both bases the same. That's the goal. And we do that by rewriting one of them, sometimes both. I'll just put rewriting. By rewriting, I guess we could put one or both. One or both. In this case, okay, let me bubble this up here. In this case, I know that 8 is a power of 2 because I can rewrite 8 as 2 to the third power. Okay, if you're not sure, if you can't see that right away, then what you can do is you can break this down into its factors, which is 4 times 2. This one is 2 times 2. So we can see that we have 3 2's, which is 2 to the third power. Okay, so what I'm going to do is I'm going to replace this 8 with that 2 to the third power. Okay, so now I'm going to have 2 to the third power equals 2 to the 2x. And since the bases are the same, I have this one-to-one property here where if the bases are the same, then the exponents should be the same, which means 3 equals 2x is all I have to solve. So divide both sides by 2, and x is equal to 3/2. Easy as that. Okay, so the way I used to teach in Algebra 2 is I would say, well, I'll just cross out the bases and look at the exponents. And you could do that too. But essentially the reason this works is because of this one-to-one property up here. Okay, let's look at one that's a little bit more difficult that has a fraction and a negative because those are always fun. So we have, I'm sorry, this thing keeps on moving on me. We have 1/3 to the power of negative x equals 27. Okay, so I know from my past, again, knowledge that 27 can be written as a 3 somehow. Okay, so keep that in mind. Okay, I'm going to change this guy I'll do some side work here, is 9 times 3, and 9 is just 3 times 3, and then there's that other 3, right? So this is 3 to the third power. Okay, so I'm going to replace that with this. So there's my first step. 1/3 to the power of negative x is equal to 3 to the third power. So now I have to figure this out because this looks a little bit weird. So here's another, I guess you could say, recall. Remember that when you're trying to make an exponent positive, all you got to do is flip the fraction. So 1/3 to the power of negative x is the same as 3/1 to the power of x. Again, if you want to make the exponent positive or negative, all you got to do is flip whatever base it goes with. So 1/3, if I flip it, that makes my x positive. Okay, so this is now going to replace this one right here. So now I'm left with 3/1 to the power of x is equal to 3 to the third. And you can kind of see what the answer is already because 3/1 is just 3, right? So 3 to the x power is equal to 3 to the third. The bases are the same, so all I have to do now is look at the exponents, which means that x is equal to 3, okay? And if you were to plug this in to check it, 1/3 to the power of negative 3, you plug it into the calculator, you're going to get 27. And that's it for that one. Okay, we're almost done with this first video. They're going to be kind of short, so luckily for you. Example number 3. So now we're going to do some actual work because those were kind of easy. Those are baby things so far. So we have example number 3, sketch on the same coordinate plane, and then we have these two functions. Okay, so these two functions they're both exponential. They have different bases. This one has a base of 3. This one has a base of 9. So what that means is that the rate at which this graph is increasing or decreasing, we'll see right now, is going by that number. So for example, if the rate was 3, that means that, think of it like a zombie, okay? If you started off with this rate, for every zombie that gets infected, 3 more people are going to get infected, and so forth. So the rate goes up at a rate of 3. 9 would be probably a way bigger rate, right? So that graph's going to be a lot steeper. So we're going to see that right now after we put our points on here. So this part right here is actually extra. I went ahead and said, well, we're going to do this, make a table. We're going to make a table with these values. And I do have to do a little bit of side work here just to kind of remind you how this works. Okay, so let's look at letter A first. So A is going to be my f of x here. Well, 3 to the negative third power, okay, that's what I have to plug in here, right? 3 to the negative third. Think of it like what I showed you on the other side. I know that, here's a side note. I'm not going to do this for all of them, just for a few. I know that 3 to the third is 27, right? But this is negative. So if it's negative, all I got to do is flip it. So 3 to the negative third is going to be 1/27. So that's my first value here, 1/27. 3 to the second power is going to be 9. But if I flip it, if I make that negative, well, it's just going to be 1/9. So this one is 1/9. 3 to the negative first power, remember, again, 3 to the first power is 3. If I flip it, it's 1/3. Easy as that, okay? This one's a little bit tricky because we tend to forget this property. 3 to the 0 power, anything to the 0 power is 1. Okay, and then we have 3 to the first power, which we already have. 3 to the second power, 9. So you can see kind of a relationship here. Hopefully that helps you with some of your problems for your homework. Okay, that it doesn't make you do so many calculations. Moving on to this one. So now we're going to go ahead and do the same thing, but for the power of 9. So I can have a different color for this one. So for this one, for letter B, okay, I'm doing 3 to the power, I'm sorry, not 3, 9 to the power of -3. So you're thinking 9 times 9 times 9, but you want to flip that. So actually, this is probably not a great color. Let me just make it a dark blue. So 9 to the power of -3. 9 times 9 is 81. 81 times 9 is 729. So we're going to flip it. So 1 over 729. They kind of look the same color. Sorry about that. But you get the idea. Okay. This one's going to be 9 to the -2 power. So again, 9 squared, if you need that, put on the side. 9 squared is 81. But we got to flip it because it's negative. So that's going to be 1 over 81. Okay, 9 to the -1st power is going to be 1/9. 9 to the 0 power, anything to the 0 power is 1. 9 to the first power is 9. And 9 squared is 81. Okay, so these are the numbers that I'm looking at. These ones and these ones when I graph. Okay, so we should notice kind of a couple things here. These are easy to get. Once you have one side, you can just flip it for the other. Okay, the y-intercepts are always going to be 1. And the reason that happens is because anything to the 0 power is going to be that 1. So as long as there's no transformations, like extra numbers here on the end, this is always going to, or any numbers in the front, this is always going to be 1. Okay, and that's what we had on our graphs previously. The y-intercept was the same for both. All right, let's go ahead and graph this. So let me go ahead and make a graph really quickly. When you make these, you typically want to make them kind of like the bottom, not too much space, because most of them are going to be up here unless you're reflecting. Okay, so we have -1, -2, -3, and then 1, 2. I just say well, up to 2, so that's okay. And then I'm going to make this next part. Let's see. We're going from super tiny numbers. So 1 over 7 to over 729 is like super, super tiny. So we're going from there all the way to at least 81. So I'm going to go ahead and do mine, we'll say maybe by tens. So 10, 20, 30, 40, 50, 60, 70, 80, 100. And if we had kept going and we had done 9 to the 3rd power, we'd have to put 729. So just keep that in mind. Okay. All right, so I'm going to go ahead and plot the first one. We have for f of x, -3 and 1/27. So 1/27 again is really small. It's probably like right here. So I don't know, somewhere there, really close to 0. And then we have -2 and 1/9. So again, it's still pretty down there. It's a little bit higher than the other one, but it's still pretty close to 0. Okay. -1 and 1/3. So that one's a little bit higher. But again, these are going to look really like almost like a line because they're so close to the x-axis here. Okay, 0 is 1, so let's just say 1 is right here. I'm just putting that for labeling purposes. 1 is going to be 3, so it's a little bit higher than that 1. And then 2 is going to be 9. So again, super tiny, kind of hard to see. Maybe we should do one more just so we can get a better idea. So let's put 3 right here. 3 to the 3rd power is 27. So this one's a little bit higher up this way. So you can see that the graph is kind of doing something like it's starting really, really close down this way. And it slowly but steady, starts to go up. Okay, and it's going to go up something like that. So of course, the more numbers you put, the better idea you're going to get here. Okay, so that's my first one, my f of x. Let's go ahead and do g of x now. And I'm going to kind of double color code this one. So the first one we have is 1 over 729, which is super like, I don't know, it's practically 0, right? It's like way down there. Then 1 over 81 is just a little bit higher. So again, it's still pretty down there. -1 is 1/9. So, sorry, hold on. Yeah, 1/9. So it's a little bit closer to that 1/3. We still have that intercept at 0, 1 here. Okay, then it starts getting interesting here at 1. So at 1, we have 1/9. So that's a little bit higher than the one I have here. And then at 2, we have 81. So at 2, I'm going to jump all the way to 81. So 80 is way up here, and it's like somewhere maybe here. And I'm not even going to bother with 3 because it's way up there somewhere. So this one is doing something kind of like, kind of hard to draw, something like that. Okay, this one was my g of x, and the other one was my f of x. Okay, so just here you can kind of see that the one that has the bigger base, so this was base of 9, okay, is definitely steeper. It starts kind of below, but it grows a lot faster because, again, the rate is bigger. 9 is bigger than 3. This one is still, it's still growing pretty quickly, but it's a lot less than this one. So there we have some examples of two graphs that we can do. I was going to have us do another one of these, but I think we get the idea on how to do these problems. So if you have some extra time, try this one. I'm not going to do it. I'm going to go ahead and leave it for you all to do. Maybe we'll do it in class, but we can try this one. Basically, it's going to be kind of the same, but notice that the powers are opposite now. So all that's going to happen is these values are going to flip. Okay, so instead of the graph going up like this, it's going to be going the other way, down like this. Okay, and that'll be example 4. So make sure, go ahead and copy it. That we'll probably do this one in class. Okay, let's go ahead and look at example. Oh, actually, I think that's it for this video because I'm going to do this from the next one. So that's it for now. Tune in for the next video. Thanks.